Hi, my name is Mike Williams. I'm the LHCb group leader at MIT, and this is a short video about how IRIS-HEP has been supporting LHCb development that's been crucial for our Run 3 trigger upgrades. In Run 3, LHCb is not going to have a hardware trigger at all. We're going to process the full LHC bunch crossing rate of events in software. So that'll amount to about 5 terabytes per second. We're going to be doing all of the tracking, all the calorimetry, and of course, a lot of aggressive selections on that in near real time. That's all going to be done on GPUs. The application is known as Allen, named after Frances Allen, who was the first woman to win the Turing Award. So in this short video, we're going to have some discussion about what pieces of that puzzle IRIS-HEP has been supporting. So first up will be my postdoc, Dan Craig, talking about a very important aspect of the Allen application, and that is data monitoring.
Okay, so Allen essentially produces 3 outputs. For events that pass a trigger selection, we record decisions and any selected objects, and these are attached to the raw events, which are then sent on to the second stage trigger. But this can only propagate information about events that pass a trigger. So we may also want information about events that fail for data quality purposes. There's a second output. This is the luminosity summary. And this is an additional data bank that's produced for a randomly selected 1 per mil of events. And as the name suggests, this is used exclusively for counters that monitor the luminosity of collisions in the detector. This covers some failing events, but for most events it's not recorded. And in any case, this isn't available in real time, which would be essential in the case of data quality issues because you want to identify them as soon as possible. So for real-time monitoring of all events, we need a third output, and this is the monitoring system which we've developed. Within Allen, most of the data processing happens on the GPU device in a number of parallel streams, and each of these is processing batches of 1,000 events in parallel. Each of these is controlled by a separate thread running on the CPU host, with data being copied back and forth between the dedicated memory of each pair. Many quantities of interest are already copied to the host memory, for example, for use in writing the trigger decisions out. So in these cases, we can write a quantity of interest directly to a monitoring histogram in the CPU memory. But in other cases, it's more efficient to first reduce the 1,000 events worth of discrete values, which we have on the GPU, into of order 100 bin accounts first. And then once we have these, we can copy them to the CPU and put them into a histogram. Once we have our histograms on the CPU, we can then use the thread-safe accumulators from the Gaudi backend to move our monitoring histograms around. Histograms are registered with the monitoring hub, which shares them with any downstream syncs. So as each thread produces its own set of histograms, we first serve these to a separate aggregation thread, which is the only sync to our first monitoring hub. And once this has combined the histograms, any histograms with the same name, we then pass that to a second monitoring hub, which serves the aggregated histograms to the monitoring system outside of Allen.
Okay, so that's where we stand on the monitoring. A lot of great progress has been made. It's basically ready to go. Something that Dan didn't talk about, which is what we want to move towards very soon, is actually doing an entire analysis using the monitoring. So our group on the physics side is very interested in dark sectors and specifically dark photons. And in the case where the dark photon has a short lifetime, each individual dark photon event would look just like electromagnetic production of dileptons. And so the rate is too high for us to keep everything, but we have all the information we need in real time. So why not just fill monitoring histogram and do the analysis on that? And so that'll be pretty exciting and something we're planning on moving towards in the next year. Okay, so next up is the group leader at Cincinnati talking about a project that they've been leading.
PV Finder is a suite of machine learning algorithms being developed to identify and locate primary vertices in LHC detectors with high efficiency, low false positive rates, and good spatial resolution. The initial focus is simulate LHCb Run 3 data. The algorithms use deep neural networks. So the figure on the left here shows a cross-section of the LHCb detector, and we want to focus our attention on the vertex locator, which is a detector, a high spatial resolution detector surrounding the proton-proton collision points. An exploded view is shown in the cartoon on the right. So the collision point, which is also called the primary vertex, is shown in the middle, and there are a series of straight line trajectories here, which correspond to charge tracks emerging from the primary vertex. They leave energy deposits in the detector. The energy deposits are reconstructed to form these straight line trajectories that we call tracks. Now, in order to locate the primary vertices with a machine learning algorithm, we generate what we call kernel density estimators. And so a small section is shown here in green. So these are the input feature sets for machine learning algorithms. And during training, we know where the real primary vertices are located. So we build what we call a target histogram, which is a Gaussian distribution around the true position. And the goal is to predict the orange histogram at the same location. And then from the predicted histograms, we will be able to extract the existence and locations of the primary vertices. We have several algorithms which do this with very different architectures. The most recent two are shown as cyan circles and as orange squares. And the efficiency of the algorithm is shown on the horizontal axis in the plot on the right, and the false positive rate on the left. And the position on this is defined by this asymmetry parameter in the cost function. And what we know is that these algorithms, both of them, produce better results than the default heuristic algorithms used by LHCb. What we want to do in the end is not to use a handwritten KDE algorithm, but to have a machine learning algorithm which starts with the track parameters. And we use the arrow ellipsoids of the points of closest approach of the individual tracks to the beamline. And we have a fully connected network, which then can predict the KDEs. This algorithm can be connected to the convolutional neural networks, which produce the predicted histograms from which we extract the primary vertices. And the work in progress at the moment is improving these algorithms for LHCb, deploying the algorithms in the LHCb software stacks in both the first level and second level trigger algorithms. And we also are adapting these algorithms to use with the Atlas and CMS experiments. Thank you.
Okay, so there you have it. That's a quick summary of the IRIS-HEP supported work on LHCb. If you have any questions, shoot us an email, and good luck with the review. And thanks to the NSF and to IRIS-HEP for supporting us.